Let's discuss what are the merits of double integration method, because you have to know where to use double integration method for a particular application. So for that, what are the merits? So the thing is, double integration, you can able to identify deflection or slope at any point in the beam, because everything is a mathematical relation. It is easy for us to identify at any point in a beam. Okay, so this is your merit. So what are the demerits? So if you look after the disadvantages, so it is very complicated to solve problems related to unsymmetrical sections or unsymmetrical loading case, something like that. So that is very important. So variable cross section also, it is difficult. Okay, it is not possible. Actually, for variable cross section, it is not possible. Whereas for unsymmetrical loading case, so you can do it, but it is complicated. So you have a very big equation, so which takes around 5 or 6 pages to solve it, and then only you will get a particular solution for this. Okay, that is the problem in double integration method. Okay, so what happens is, so mathematicians, they identified a new methodology to clear this particular problem. So they introduce this method, which is called as Macaulay's method. So it is like another version, as I told you. So it is a double integration method. Whatever we apply for double integration, same approach we are going to do, but with few rules. So there are some rules which we have to follow, and we can able to do that. So this can be used for unsymmetrical loading cases. So loading, eccentric loading case, or 2 or 3 loads, even for that case, you can be able to solve using this Macaulay's method without any complications. What are the rules? The first one, you have to consider a section line covering all the load. That is the first step. So previously in double integration, I have shown a problem. So considering x section at any point, either after the load or before the load. So we solved in both ways and we got the solution. But in this Macaulay's method, you have to consider only after completing all the loads. So when I talk about load, it is only the load which is acting on the top side, not the reaction. Reaction on the number contributed. So we should not consider that. You have to consider only the load which is at the top side. So that is important. Okay, that is the first rule. The second rule is, you are going to draw a line which is called as a Macaulay's line. So we are going to draw a line which is a Macaulay's line. So we are going to use this Macaulay's line to split the equation under different loads. Okay, so I will explain it with an example. So a Macaulay's line is drawn and I am splitting the equation under different loading cases. So what happens? Why we are doing this? So that is the next one. We use Macaulay's line to reduce the equation based on the boundary conditions or based on the values you need. For example, I need x is equal to at a particular location. For a particular location, we reduce the equation, overall equation, by applying the Macaulay's line, and we will simplify the equation and we will solve it. That is the main purpose of this Macaulay's line. Okay, so this is what we are going to do. And there is another rule for UDL and other loads, so which we will be discussing while we are solving the particular problems. Mainly these 3 rules for any point load, or what, even for UDL, we are used these 3 rules. But UDL, you will have additional rule. Let me consider this is my beam, a simply supported beam, having 3 loads. You can able to see there are 3 loads which is acting here. So W1, W2 and W3. These are the 3 loads we have. And you can able to see the overall length of my beam is around 10 meter. So 3 meter up to W1 and another 4 meter from W1 to W2, 1 meter from 2 to 3, and later you have 2 meters. So totally, so 3 plus, so you have totally 10 meters. And let me consider your reaction. So let me, it depends on the loading cases, you will identify the reactions. And let's consider this case. So let me apply the first rule. Consider the section line by covering all loads. So you have three loads, W1, W2, W3. So where I have to take the section, I have to take the section only here, right? I should not take here or here or here. The rule is you have to cover all the loads, which means my XX has to be here. So this, I will consider this portion as X. Right? This portion, I will call it as X. Now, let us identify what will be the dimension for other cases. For example, let me consider what will be this distance for this particular thing. So this is X minus 3, right? So next, what about this one? It is X minus 7. So you have X and 7 is gone. So this will be X minus 7. So the next one is this particular thing. What is this value? So this will be X minus 8, remaining term. So you have for RA load, you have X minus 3 for W1 load, you have X minus 7 for W2 load, and you have X minus 8 for W3 load. So why I am doing this? Because I'm going to take moment. So moment at any point, I'm going to take moment at X. If I take moment at X, it is forced into perpendicular distance. So I need distance at each loading cases. That is why I am writing here. Okay. So let me consider. So I am identifying what is my MX. Okay. Let me go for the second condition. Second rule. So use Macaulay's line to split up the equation under different loads. Okay. First, let us write what is my Macaulay's line. My moment at point X will be equal to, so force into perpendicular distance. We will start from here. Always start from left to right. So I am solving it from left to right. When I solve from left to right, clockwise rotation has to be considered as positive and anti-clockwise rotation has to be considered as negative. Okay. So RA, so force into perpendicular distance, RA into X. Let me go for the next one. W1 into X minus 3. What is the rotation here? It is rotating in anti-clockwise. So X is the fixed point and W1 is the force which is acting, which is rotating in anti-clockwise. So minus W1 into X minus 3 minus W2 into X minus 7. Okay. Next, minus W3 into X minus 8. Since we are taking moment this side and we are identifying bending moment from left to right, we should consider only the left hand side load. We should not consider the right hand side load. So only up to this, that's it. Now we will concentrate on Macaulay's line. What is this Macaulay's line? Wherever you have the change in X value, you have to draw a line, that's it. So you have X here. Here we have X minus 3, which means I have to draw a line here. Similarly, this is X minus 3, whereas here it is X minus 7. So there is a change. X minus 3 is different, X minus 7 is different. So I have to draw a line here. X minus 7, X minus 8. So I have to draw a line here. This line we call it as Macaulay's line. We will go for the last rule. Use Macaulay's line to reduce the equation based on the boundary condition. So the reason why I split this is, we call this line as a boundary lines, which means whenever I consider X, I have to consider my conditions from 0 to, what is this value? 3, right? So after X, you are having 3. So X minus 3, when I put 3 here, it becomes 0 here. So 0 to 3. The first line will be from 0 to 3. After 3, so 3 it becomes 0. When it is 3.1, it is a positive value, right? So from 3.1 to 7, you have 7 here, right? After this 3, you have 7. You have to consider this boundary condition. So similarly here, when 7.1 to, the next one here is 8. You have to consider this. From 8.1 to The beam total distance is 10. So 8.1 to 10. You have to consider this. Any doubt in this? Still, I have not completed. What it says is, I should not have any negative terms here. When I put x is equal to 1, let me consider my x is 1. So here, this term is having a positive value. Don't look after this negatives, leave it. I am concentrating only on distances. Okay, so 1 is positive here. Here, 1 minus 3, it is minus 2, negative here. So which means I should not consider this. Similarly here, 1 minus 7, negative here. We should not consider this. 1 minus 8, again negative. We should not consider this. Okay. When I consider x is equal to 4.5, for example, 4.5 is x is 4.5 positive. You have to consider this. 4.5 minus 3, again it's a positive value. You should consider this also. Here 4.5 minus 7, negative value. You should not consider this too. So my equation will be up to this. So this condition, reduce the equation based on boundary conditions. For example, my boundary condition when x is equal to 0, y is equal to 0. Then we consider this is my boundary condition. So here x is 0. Of course, x 0 is not positive or negative. So it is both. So let me consider this. 0 minus 3, negative, negative, negative. So my equation is mx is equal to rax. That's it. Right? I should not consider this other equations. Neglect all the equations. Let me consider x is equal to L by 2, which is 5. dy by dx is 0. Something like this. Right? Let me consider. So either random or actually for this loading case, you won't get dy by d is equal to 0 at 5. Just for learning purpose, I am writing it. So when I say x is equal to 5, dy by dx is equal to 0. 5, when I substitute x here, 5, positive value, you will consider this. 5 minus 3, 2, positive value, we will consider this. 5 minus 7, negative, you should not consider. This is also, you should not consider. So my equation is mx is equal to rax minus w1 x minus 3. That's it. Other things has to be neglected. Okay. This is also applicable to identify your deflection. For example, I want what is the deflection at 6 meter, right? In that case, what is the equation I have to consider based on the same procedure what we follow? It is also applicable for deflection plus deflection. Okay. So when I say that, when I say x is equal to 6, I should know what is my y value. X is 6, positive value applicable. 6 minus 3, positive value applicable. 6 minus 7, negative, negative. So my equation has to be this one. Mx is equal to rax minus w1 x minus 3. That's it. And use that equation to substitute the value x is equal to 6. You will get what is your deflection. Okay. Let us consider what is this mx? Ei or y by dx square. This is my moment. So if I want slope, I will integrate this. You will get dy by dx. Similarly, if I want deflection, I will integrate again. I will get y. Okay. So the thing is, when I integrate this, I will get a constant. My question is, where you put the constant? Which line? So whether I have to put it here or here or here. So always you put the constant at the beginning stage, right? Always your constant will be at the first one. You should not put the constant at the last. Okay? All constants should come in the first line, before that first line. So this is a 16 mark problem, simply supported beam. So the length of the beam is 4 meter long. It carries two concentrated loads, which is 12 kilonewton and 8 kilonewton, acting like this. You have to identify what is the deflection at point C and deflection at point D. That is the question. They are given what is the value of Young's modulus E and what is the value of your moment of inertia I. Let us solve this. Before that, you have to think about your unit. Most of the cases we will be using in meter and kilonewton. So I will fix my unit as kilonewton and meter. Okay, don't go for mm because you will get a very large number. So even this 3 will become 3000. So you may miss some zeros, right? While you are writing it, if for the next step you will miss some zeros while writing in while doing in mm, right? So best prefer kilonewton and meter. So this kilonewton depends on the loading conditions. If the loading is Newton, you put it as Newton and meter. That's it. Okay. So my unit is kilonewton and meter. So the next step, step 2, what I have to do is I have to convert this EI, because I'm going to solve. My formula will be in terms of EI d square by dx square. So E and I is multiplied together. So let us identify what is this E and I. Let us multiply it. E is 200 gigapascal, which is 200 into giga is 10 power 9. Pascal is Newton per meter square. So your unit is Newton per meter square. Okay. So I will write, just for reference, I am writing it Newton per meter square. Okay. Next, I value. I is 160 into 10 power 6. And this is in mm power 4. So most of them will make mistake here, because I made my unit as kilonewton and meter. So you convert everything as kilonewton and meter to solve it. So நிறைய பேர் இந்த இடத்துல மிஸ்டேக் பண்றாங்க. அதுக்கு தான் நான் வந்து ஸ்பெசிஃபிக்கா I am concentrating on this. Okay, let me consider EI here again. I am going to convert this Newton to kilonewton. What I have to do? I have to take this 10 power 3 outside. Right? I have to take 10 power 3 outside. So remaining will be 200 into 10 power 6. Right? So 9 la 3, I am subtracting 3. So I am getting 6. So this is now in kilonewton and meter square. Right? So this is over. I converted this. Okay, now I will concentrate on this one. I will write this entire thing 160 into 10 power 6. Now I'm going to convert this mm to meter. Right? When I convert to mm to meter, what happens is you have to multiply with 10 power minus 3. So I have to multiply with 10 power minus 3. So divided by 1000, right? But this is mm power 4. So which is 10 power minus 3 power 4. So this will be in meter power 4. So what will get? So let me complete this. So 160 into 10 power 6 into 10 power minus 12. Because it is in power, we have to multiply 10 power minus 12. So kilonewton meter square. Right? So what is the value? So this is my value. So it is around 32,000 kilonewton meter square. Okay. So I am going to use this only at the end, not now. So I will consider as a variable. I will be solving it. Right. Don't substitute it at the beginning itself. You have to use it only at the end. Okay. So that is very important. Now, first I have to identify what is my reaction. What is my reaction? RA and RB. Same engineering mechanics problem. So I say that this is in equilibrium state. When I say it is in equilibrium state, I can say that sigma fx is equal to 0. So horizontal force, vertical force is zeros, which means upward force is equal to downward force. So we have two upward forces, force which is going towards upward direction, which is RA and RB. So this RA plus RB will be equal to your downward force. Downward force is 12 plus 8. So totally 20. So I'll call this as equation 1. Next, moment at any point is equal to 0. Let me take moment at A and equate it to 0. So I am doing it to identify the reaction. Don't think about whether it has to be clockwise or anti-clockwise. It is your wish. You can consider clockwise as positive or anti-clockwise is positive. Both you will get the same result. Okay. Let me take moment at is equal to 0. So usual step is I will take anti-clockwise as positive and clockwise as negative. So while taking these things, when I take moment at A is equal to 0, RB is rotating in anti-clockwise direction. RB into 14. So I'll get RB into 14 minus this one, 12 into 3, rotating in clockwise, minus 12 into 3 minus 8 into, so 3 plus 6.5, which is 9.5. So this is equal to 0. So I have only 3 forces. I'm taking moment for this 3 forces. For this force, 12 into 3. For this force, 8 into total distance, 9.5. And for this force, it is 14. Right? So what will be your RB? So RB is 8 kilonewton. So in that case, RA will be 12 kilonewton. Right? So I identify the value. So this one is 12 and this one is 8. Now I'm going to consider the section. Where you have to take the section? Right? Let me consider a section here. Okay. So in that case, let me tell me what are the values. I'll call this as X. This is X. Next, from here to here, it is X minus 3. 3 is gone. So similar to what we have done previously. And for this, it is X minus 9.5. So let me identify. So moment at any point X is equal to, I'm taking moment at the point X, which is equal to 12 into X. Rotation is clockwise. Clockwise is positive. Okay, for this condition. So we are moving from left to right. When I move from left to right, clockwise is positive. Okay, so which is 12 into X. 12x. Next, minus, others are negative, which is in anti-clockwise, minus 12 into X minus 3 for this, 12 into X minus 3, and for this 8 into X minus 9.5 minus 8 into X minus 9.5. I'll put it here. Only thing is I have to change it accordingly, so I don't want this mx. You know that what is this mx? Mx is ei d square by dx square. This is my mx. Now I'm going to split this. This is x here, this x minus 3. So I have to split here, right? So I will draw a line, Macaulay's line here. Okay. Similarly, I have another one here. So this is x minus 3 and this is x minus 9. So I have to split here also. Right? So these are my two Macaulay's line. Okay. Now, so the procedure is same what we do in double integration method. So only thing is I have to integrate this. So I integrate once. I'll get ei dy by dx, which is equal to 12. Integrating x, you'll get x square by 2 plus c1. As I told you, you have to put that c1 before itself. Minus 12. This is the entire variable. Don't separate it. So last class I told you in double integration, whenever you have a term x minus 3 or x minus 9, is an entire variable. You can consider this as capital X. So when I integrate capital X, you will get capital X square by 2. So I have to integrate like that. Okay. Don't separate this. Okay. So minus 12, x minus 3 the whole square divided by 2, right? Minus 8, this will be x minus 9.5 whole square divided by 2. So again, I forgot about that lines, right? So you have that Macaulay line. I will get a Macaulay line here. We'll get another Macaulay line here. Let me simplify this. So I will get EI dy by dx. This will be 12 by 2. We'll get 6x square plus c1 minus again 6 x minus 3 the whole square minus 4 x minus 9.5 the whole square. So this is my term. So this term is your what you can say slope equation. This is my slope equation. So I'll call this as slope equation. Let me call this as equation 1. I think already I put equation 1, right? So this is equation 2. Okay. Now, again, we will integrate this because I need what is my deflection y. Integrating it again, you'll get EI y will be equal to 6 x square. Integrating it, you will get x cube by 3 plus c1, you will get c1x plus c2 minus 6 x minus 3 the whole square. What will get? You will get x minus 3 the whole cube divided by 3 minus 4 x minus 9.5 the whole cube divided by 3. Okay, this is my equation. We'll get EIY is equal to, so this will become 2x cube plus c1x plus c2 minus 2 into x minus 3 the whole cube minus this. Don't need to do it in fraction. I will consider 4 by 3 itself. Yeah, so 4 by 3 x minus 9.5 the whole cube, right? So this is my deflection equation. I will consider this as equation 3. Now comes the main thing. I have to apply boundary conditions. I have to concentrate on boundary condition. What is the boundary condition for this? Can you tell me what will be the boundary condition for this particular problem?
X is equal to 0, y equal to 0.
Yeah, very good. Then?
Dy by dx is equal to maximum.
No. That we can't apply. Right? Because it is very, very unsymmetrical rule. Right? So my conditions will be when x is equal to 0, y is equal to 0. And the second condition is when x is equal to 14. I think the entire beam size is 14, right? So when x is equal to 14, y is equal to 0. So this is my boundary condition. Okay. So I'm going to apply the first boundary condition. So let me consider when x is equal to 0, y is equal to 0. So I have y term here, which means I have to use equation 3 because that is having y, right? So equation 2 does only has dy by dx, which is slope. So I'm going to apply only equation 3. In equation 3, according to the boundary condition, I have to change my equation. So x is 0. So what will be my equation? I have to write the equation. My equation will be EIY is equal to 2x cube plus c1x plus c2. That's it. Because when x is equal to 0, when I substitute, this will become zeros. That is enough. This is a negative term. 0 minus 3. As per Macaulay's rule, you should omit whatever which is having negative terms in the distance. So this is negative. This is also negative. I am omitting it. I apply boundary condition only for this. If I apply x is equal to 0, y is equal to 0, what will get? So 0 is equal to 0 plus 0. So C2 is equal to 0. You'll get C2 as 0. So we completed that part, right? So this is over. Next, second boundary condition. When x is equal to 14, y is equal to 0. What is my equation? When I substitute x is equal to 14 here, we are getting a positive value, okay. 14 minus 3, again a positive value, okay. 14 minus 9.5, that is also a positive value. So what will be my equation? I have the entire equation. So my equation is EIY is equal to 2x cube plus C1x. I am omitting C2 because C2 is 0. Omitting C2 minus 2 into x minus 3 the whole cube minus 4 by 3 x minus 9.5. This is my entire equation, right? So C2, since it is 0, I neglected. So this is my value. Let me substitute. What is when x is equal to 0? Sorry, x is equal to 14, y is equal to 0. What will get? 0 is equal to 2 into 14 cube plus C1 into 14 minus 2 into 14 minus 3, you are getting 11. So 11 cube minus 4 by 3 into, so 14 minus 9.5. So you are getting 4.5. I think I missed something. 4.5 cube. I missed this cube. Yeah. So 9.5 cube, right? So that one. Yeah. So can you substitute and identify what is the value of C1? I'll get C1 is equal to minus 210.5. So this is my C1 value. Okay. So now I have to rewrite my equation. What is my slope equation and what is my deflection equation, right? In this case, you have to look after it. So to save your time, look at the problem and decide which one you have to write. So the problem. So does the problem ask you to identify slope? No. So the problem asks you to identify only deflection. So no need to write your slope equation then. Okay. You can write only the deflection equation. That is enough. Okay. What is my deflection equation? Okay. This is my entire equation. So for better, I will copy this. So only difference is I identify the values of this thing minus 210.53x. This is my deflection equation. Any doubt in this deflection equation?
So actually the C1 value is 193.
You are getting different C1 value.
Yes, sir.
Yeah, minus 193.
17 minus 193.1.
178.
Okay. Thank you. So this is my value, right? So which means this will be minus 193.17x. Okay, this is my deflection equation. So now they are asking to identify what is the y value at C and D, right? Okay, let me identify deflection at C. Deflection at C, right? When I say deflection at C, my x value is 3 meter, right? Similarly, when I say deflection at D, my x value is 9.5 meter. So to identify deflection at C, I have to substitute x is equal to 3 to identify your y value. Okay, so since my x is equal to 3, what will be my deflection equation? That is important. So 3, again, you should follow the same rule. 3, when I substitute 3 here, positive value, very good. This one, 3 minus 3, 0. So that means you can't, you don't need to consider this. This is a negative value. You can't skip this 2. EI y is equal to 2x cube minus 193.717 x. That is my equation. Here, substitute x is equal to 3. So I'll get EIY is equal to 2 into 3 cube minus 193.17 into 3. You will get what is the y value, EIY. So you will get this. Then you can identify y at C. Substitute the end. What is your EI value, which we identified at the beginning stage. So we identified 32 into 10 power 3, right? You have to substitute it here. Okay. We are getting minus 16 point.
Minus 16.422 into 10 power minus 3
Minus 3 meter.
meters.
Yeah? Yeah, very good.
Sir, minus is for downward direction, sir.
Yeah, minus indicates the deflection is towards downward direction. So what is this value actually? 2 into 3 cube minus 193.17 into 3. Minus 1104.8. Okay? Right. So similarly, to identify deflection at the D, location D, what you have to do? You know what you have to do, right? So you have to substitute x is equal to 9.5, right? So x is equal to 9.5. So when you consider x is equal to 9.5, my equation is till 1 and 2. So 2x cube minus 193.17x minus 2 into x minus 3 the whole cube. So that is my equation. So you have to use that equation and you have to find out what is the deflection.